Have you ever wondered why the solar panels on your roof can convert sunlight into electricity? It's all thanks to a fascinating phenomenon called the photoelectric effect. This scientific marvel is responsible for converting the sun's radiant energy into usable power, making our lives greener and more sustainable. It's not just about solar panels though. The photoelectric effect is everywhere, subtly influencing our world in countless ways. So buckle up as we dive deep into the world of electrons, light and energy conversion. Welcome to the intriguing journey of the photoelectric effect. Imagine you're a photon, a particle of light, cruising through space at the speed of light. Suddenly, you crash into a metal surface and knock an electron right off its atom. Congratulations, you've just experienced the photoelectric effect. Now what just happened here? Well, you, as a photon, carried a specific amount of energy which we like to call a quantum. When you collided with the metal surface, you transferred that quantum of energy to an electron in the metal. This energy was just enough to overcome the electron's bond with its atom, and voila, the electron, now free, zips off into the world. This phenomenon, my friends, is what we call the photoelectric effect. The term photo refers to light and electric hints at the electrical energy that's produced when the freed electron starts to move. Put simply, the photoelectric effect is the process where light energy is converted into electrical energy. But here's the catch. Not all photons can knock electrons off their atoms. The photon needs to have a minimum amount of energy, known as the threshold energy, to set the electron free. If the photon's energy is less than this threshold, the electron stays put. No energy conversion, no photoelectric effect. It's like trying to push a heavy boulder. You need to exert a certain amount of force to get that boulder moving. If your force is less than what's required, the boulder won't budge. Same principle applies here. Another interesting point is that the number of electrons that get knocked off is directly proportional to the intensity of light. More intense light means more photons, which means more electrons being knocked off their atoms. But remember, the energy of the photon determines if an electron can be knocked off, while the intensity of light determines how many electrons get knocked off. So, in simpler terms, the photoelectric effect is all about light energy being converted into electrical energy. But you might ask, does the intensity of light or the frequency of light matter in this process? Well, they do, and in quite a surprising way. Imagine a locked door. The key to this door is the frequency of the light. If you have the correct key, you can unlock the door, regardless of how gently or forcefully you turn it. This is similar to how the frequency of light can knock off electrons from a metal surface in the photoelectric effect. If the frequency of light is high enough, think about a key perfectly matching the lock. It can effectively knock off electrons, regardless of its intensity. Now, consider the intensity of light as the number of keys you have. If you have more keys, you can unlock more doors at once. Analogously, a higher intensity light means more photons are hitting the surface, which can increase the number of knocked off electrons, but only if the frequency is high enough to knock them off in the first place. So, in simpler terms, high frequency light has the power to unlock the electron door, while high intensity light is like having more keys to open more doors. But what about the energy of the knocked off electrons, you wonder? Well, that's where the stopping potential and cutoff voltage come into play. The stopping potential is the minimum voltage needed to stop the fastest moving photoelectron, while the cutoff voltage is the minimum voltage at which photoelectric emission occurs. In both cases, the energy of the photoelectrons is determined by the frequency of light, not its intensity. The higher the frequency, the more energy the electrons will carry when they are knocked off. And the threshold frequency? That's the minimum frequency of light required to start the photoelectric effect. If the light's frequency is below this threshold, no electrons will be emitted, no matter the intensity. So it's not about how hard the light hits, but how fast it moves that determines the success of the photoelectric effect. Fascinating, isn't it? Now, who better to explain the photoelectric effect than the genius himself, Albert Einstein? Einstein, with his razor-sharp intellect, delved into the mysteries of the photoelectric effect and came up with a set of postulates that forever changed our understanding of light and energy. Einstein's first postulate was that light is composed of discrete packets of energy or quanta. He referred to these packets as photons. This was a revolutionary idea. Instead of viewing light as a continuous wave, as was the common belief, Einstein proposed that light was also particulate in nature. Each photon carries a specific amount of energy directly proportional to its frequency. This was the birth of the concept of duality in the nature of light. His second postulate was that these photons could interact with electrons in a one-on-one encounter. When a photon with enough energy comes into contact with an electron, it can transfer its energy to the electron. This energy can then be used by the electron to break free from its atom, resulting in the photoelectric effect. The third postulate stated that the energy of a photon is given by a simple equation. The energy equals the frequency of the photon multiplied by Planck's constant. The energy of the photon must be sufficient to overcome the binding energy of the electron, known as the work function. Any excess energy appears as kinetic energy in the ejected electron. Finally, Einstein postulated that the emission of electrons begins as soon as the light shines on the metal surface. There's no time delay. This was a significant point because it contradicted the wave theory of light, which predicted a delay between the light's incidence and the electron's emission. Einstein's postulates were revolutionary and faced a lot of resistance initially, but as more experiments were conducted, the evidence piled up, and the scientific community had to accept the bold ideas put forth by Einstein. And that's how Einstein, with his brilliant mind, gave us a deeper understanding of the photoelectric effect. So, is light a wave or a particle? Well, it turns out it's both. This mind-bending concept is known as the dual nature of light, a cornerstone of quantum mechanics and a key player in the photoelectric effect. Now, how can something be both a particle and a wave? Let's imagine light as a wave first. This wave model is pretty handy when we think about phenomena like diffraction, interference, and polarization. In these cases, light behaves like ripples on a pond, spreading out and overlapping to create intricate patterns. But then there are moments when light acts more like a party crasher, barging in with a sudden burst of energy. This is where the particle model comes in handy. Light can also be described as a stream of particles or photons, each carrying a discrete packet of energy. This particle-like behavior helps us understand the photoelectric effect, where light hits a metal surface and knocks electrons loose. The dual nature of light isn't just a quirky theoretical concept, it has practical implications too. Let's take solar panels for instance. These devices capture sunlight and convert it into electricity. But how does that work? Well, when photons from the sun hit the solar cells, they behave like particles, transferring their energy to the electrons in the material. This energy kickstarts the electrons, causing them to move and create an electrical current. However, it's not all smooth sailing. There are still questions that baffle scientists. For example, how can light be a wave and a particle at the same time? How does it decide when to behave like one or the other? As it stands, these questions remain some of the great mysteries in the world of quantum mechanics. So, to wrap up, light is both a wave and a particle, and this dual nature is absolutely crucial in understanding the photoelectric effect. As counterintuitive as it may seem, this dual nature of light is what makes the photoelectric effect, and by extension, our solar panels, possible. So, there you have it, the photoelectric effect in all its glory. We've traversed an enlightening path from the simple concept of a photon knocking off an electron to the deeper intricacies of the photoelectric effect. Let's do a quick recap. We started with the photoelectric effect, a phenomenon where electrons are ejected from a material, typically a metal, when it absorbs energy from light. We then delved into the relationship between photoelectrons and the intensity and frequency of incident light, understanding how the intensity influences the number of photoelectrons while the frequency determines their kinetic energy. We also explored the concepts of stopping potential and cutoff voltage, which are crucial in determining the maximum kinetic energy of ejected photoelectrons and the minimum frequency of light required to cause the photoelectric effect, respectively. Next, we dived into Einstein's postulates, which brilliantly explained the photoelectric effect using the idea of light behaving as particles or photons, each carrying a quantum of energy. This led us to the fascinating concept of the dual nature of light, which exhibits both wave-like and particle-like properties. This journey has been an exciting ride, unmasking the wonders of light and its interaction with matter. The next time you see a solar panel, you'll know the fascinating physics that makes it work. Until our next journey, stay curious and keep exploring.